Hello guys. So today I'm gonna talk about statics, forces and moments. So first we're gonna learn what forces and moments are and how they are different and how they are related. Then how to draw a free body diagram and why you should for every problem. And how to add forces and moments and what you can learn by doing so. The study of statics might seem more important for civil engineers than mechanical engineers. After all, mechanical engineers make things that move. So why bother studying how to analyze things at a standstill? The fact is that not only do the tools of static provide an excellent stepping stone to studying dynamics, fluid mechanics, and other mechanical disciplines, they're useful in everyday practice in their own right. So in this section, we'll start by introducing the concepts of forces and moments. Nearly every facet of mechanical engineering depends on these concepts. We will then learn to draw free body diagrams. Then these idealizations of the problem at hand are the first step in solving nearly any engineering problem. We will finish by showing how to add forces and moments together and what we can learn about real-life problems by using so. So, forces and moments. Two simple examples can be used to demonstrate the difference between these two concepts. All three represents the action of one body on another, but the type of action is different. First is force. The more straightforward of the two. Its meaning in engineering is closely aligned with the meaning in everyday use. The hammer in the picture here is applying a force to the nail. As you can see, the force can be represented as a vector with the same direction as the motion of the head of the hammer at the time of impact. Second one is moment. Newton's second law is usually thought of as applying to straight line motion. It can be applied to rotational motion as well. Rather than linear force, we require the concept of a moment. For now, think of it as a rotational force. The moment about a particular axis can be found using the following equation, which is moment equals to r times f, where r is a vector that connects the points where the force is applied to the axis of the rotation. The knot in the figure at the right, as you can see, has a moment applied to it by a spider wrench. It is important to always designate the points about which the moment is taken. That is, what is the center of the rotation. Okay, here we have an example. You want to find a moment. Question is, the mechanic in the picture above is applying 50 Newton with each hand, and his hands are 0.2 meter from the axis of the wrench. The knot is at point A, as you can see. So we have two forces, one downward and one upward. And A is the center of the rotation. Therefore, the moment is M equals to 2F times R. Now, why 2? Because we have two forces, and each force is at the 0.2 meter distance from the center of the rotation. Therefore, we multiply by 2. So it's twice of the force, which is 50 Newton, times twice of the distance, which is 0.2 meters. And therefore, the answer is 20 Newton meter. There is an important simplification in this problem. Both forces were perpendicular to the r vectors. If they weren't, we'd find the component of the vector that was perpendicular first and then find the moment. Now here we reach to drawing a free body diagram. Drawing a free body diagram has many benefits. One is to help you to clarify, identify what you know and don't know about the problem. It helps you to clearly state your assumptions. A free body diagram makes it easier for others to follow your work, and it makes it easier for future you to follow your work if you have to review it 6 months or 6 years ago. 6 years later. Yeah. Industries where safety and government regulations are extremely important, such as aviation or nuclear power, it is not uncommon to review 25-year-old hand calculations in the event of a proposed design change or an accident. So the procedure can be summarized as follows. 1. Select which parts must have their geometry included in the sketch and which parts can have their impact on the problem represented as forces or moments. This process is sometimes visualized as drawing a circle around the problem so that things inside the circle is represented as geometry and things outside the circle are represented as forces applied to the parts inside the circle. Second, sketch the geometry inside the circle, and third, draw arrows to show where forces and moments are being applied and label them with the magnitudes of the forces. So let's do an example of box on a slope. So first I'm gonna draw a boundary around the box. We won't analyze the slope, we want to know what is happening to the box. Perhaps we want to determine if it will slide or how much force would it be needed to make it start moving. Second, we're gonna draw the geometry, and third, the vectors for any and all possible forces. The first one would be the weight of the box, which can be modeled in the middle of the box, assuming that the density of the contents of the box are uniform. And as you know, that weight is equals to mass times gravitational force. And there are other two forces. The first one is the normal force, which is also called as reaction force. It's the same amount of the weight and in opposite direction. And finally, there will be the friction force, which is tangent to the surface, and it should be opposite to the motion. Let's look at another example, a bridge. So I assume that support for the base at 2 points on each end. The bridge is so narrow that the cars drive down the middle, again leaving us with the symmetrical part. This is not such a big assumption. The method is easily extended to 3D, but is much harder to draw it on a whiteboard, so we just go with it. A car is driving along the road and it is accelerating, which puts a force on the road in the opposite direction. And it is front wheel drive. So we go as the steps. The first step was to drawing our boundary. We won't analyze the road. While it may move more than a ratio from the previous example, we're probably interested in how well we have to attach the bridge to the ground. So drawing our circle around that interface allows us to see what forces are being applied there. Second, we will draw the geometry. Since there is a plane of symmetry, draw it from the side. Show the road support connections with little triangles. And third, draw the vectors for any and all possible forces. So first one would be the weight of the car, which is spread over 2 wheels. The acceleration force is applied to the front wheel. The weight of the bridge is represented as a force in the middle, and the connection to the road will show as 3 different reaction forces. One in the x and y direction on the left, but only in the y direction to the right. It's very common assumption in academic problems. The problem is much easier to solve and not much information is lost. You'll see why in a little while. Also note that we assume directions for the forces at A and B. If we guessed wrong, the forces we find will be negative. So imagine the bridge without cars, traffic or wind. It is just sitting there. Often we draw two diagrams, one for the geometry and one for the forces. Also note that all dimensions starts from a common origin. Let's do another example. A diving board. Assume support for the base at 4 bolts. The diver stands in the middle of the board at the end, so there is a plane of symmetry through the board. The force on each pair, front and back, of the bolts will be the same. Step 1, draw our boundary. Step 2, draw the geometry as you can see in the picture. And step 3, draw the vectors for any and all possible forces. The weight of the diver is easy. The bolted connections will show as a force and a moment. Also note that we assume the direction of the force and moment at B. If we guessed it wrong, then the force and the moment we calculate will be negative. So to sum of all forces and moments, it should make intuitive sense that if an object at rest is subjected to two equal and opposite forces, then it will not move. Similarly, if a string wheel of a car is pulled with equal force in two directions, it will not rotate. These are just special cases of Newton's second law. The full version of the law is that force is equals to mass times acceleration. As you might expect, in the case of statics, there is no movement and thus no acceleration. Therefore, force would be 0. Now we need to be clear that force is the net or total force, not just sum of the force applied to a part. It is more clear and more traditional than to write it in this way. So net force must be equal to 0. Force here are individual forces which are added together by the summation sign. We saw in the section on vectors that vectors can be added together easily. So this is no problem for us. The next step is to notice that the vectors are 3D. So we have x direction, y direction, and z direction. And in all of those directions, our total force must be equal to 0. That gives us 3 equations to use for any situation. What about rotation? Static means no rotation either. Following a similar line of thought, don't want to bother explaining rotational inertia, we get that the total moment in x direction, y direction, and z direction is also equals to 0. So therefore at the end we have 6 equations in total, which we will use these equations to solve many important problems. Let's go back to the box on a slope example. So find the forces being applied to the box by the slope if the box is about to slip but hasn't yet started moving. For this example, we'll assume that the mass is 10 kg and the gravitational force is 9.81 meter per second square, and it's at the slope of 30 degrees. So first we're going to draw the free body diagram, write the governing equations. So the total force in x, y, and z direction must be equal to 0. Don't forget that the total moment in z direction must be equal to 0 as well. Then start applying the equations. So in the x direction, I have normal force times cosine of 60 degrees minus the friction force, which is in the opposite direction, cosine of 30 degrees. It has to be equal to 0. And if I rearrange it to find for the friction force, that would leave me with friction force equals to the normal force, cosine of 60 over cosine of 30, which will be n as normal